All right, welcome to week 10 problem solving session for Introduction to Wireless and Cellular Communications. I'm your TA Sachin from the Indian Institute of Science. I'll be attending a conference next week in Australia, so next week's class has been shifted to today. Okay, we have been given a fourth degree primitive polynomial 1 plus x power 4. We have to um, check which is the correct feed forward shift register representation of the given primitive polynomial. And three options have been given. Four options have been given. Last option is none of the above. So you have four, since it's fourth order, fourth degree, uh, the polynomial just tells you the connections that are present. So you have an adder in each case. The polynomial will tell you which of the connections are present, which of the delayed versions are added to the adder. So this is x square, x cube, and x power 4. The polynomial is 1 plus x power 4. So we have a connection from direct connection, and we have a connection from x, and we have connection from x power 4. You could write it this way. So, depending on whether a term is present or not, you'll close the switch. So that term will be added to your adder. There's a one term, there's an x term, then there's x power 4 term, and there's no x square term and there's no x cube term. So actually, you can get rid of the adder at x square and x cube. So I'll simply write an action is made with the adder if the coefficient of the corresponding term in the polynomial is 1. Two is for the above question with the initialization of x1, x2, x3, x4 equal to 1, 0, 0. What is the output M sequence? Since this is your assignment question, I'll change. I won't answer the same question. So I'll just change the circuit. I'll show you how to do it. You have to do it for the circuit in question 1. For the below circuit, I'll draw the let's say this is what we had. I'll give you a few minutes. Why don't you try and get the answer? Then I'll come back and tell you the answer for this question. Okay, we need to make a to answer this question. You just make a table of sorts. I.e. x1, x2, x4, then your output. Your output is x4. Initially, you are initializing x1, x2, x3, x4 to 1, 0, 0, 0. Then, when a clock pulse arrives, these are delay elements, so they're you must have seen in digital circuits, they're synchronized. They'll work based on clock pulses. So they're triggered when a clock pulse arrives. So initially, since x4 is 0, the first output will be 0. And at that time, the input IA is here in for this circuit, IA is x2 plus x4. It is 0 plus 0 is 0. Now, when the clock pulse comes, it will give the output as 0 and shift the states will be shifted. So this 0 which is present here will go to x1. And then this 1 that is here will go to x2. So the state is shifted to 0, 1, 0, 0. So this thing got shifted by 1 bit, and then this comes out as the output. Now the new input when it when the new state x1, x2, x3, x4 is 0, 1, 0, 0 is new input is x2 plus x4, which is 1 plus 0, which is 1. Now when a clock pulse comes, this 1, 0, 1, 0 is shifted to x1, x2, x3, x4, and the x whatever is there x4 will be given as output. Now the new input is x2 plus x4, 0 plus 0, 0. Again the same thing, just repeat. Output is 0, 0, 1, 0, 1. X2 plus x4 is now 0. Next clock pulse output is 1, 0, 0, 1, 0. And 0, 0, 0, 0, 1. And 1, 1, triple 0. And so on. So you keep going like that. Now this is for this particular circuit. Your assignment, you first have to answer question 1 and get the circuit first. Then you do the same thing. Use the same procedure. You will get the output sequence. So this circuit is option B of your first question. If they answered to the first question option B, then this will be the answer. If the option to the first question is A or C, then you have to write a similar type of table for circuits in A or C, and then you will get the corresponding output. DSSS with a length of spreading sequence Q. Which of the following is true regarding the frequency response of the DSSS pulse shaping signal? Okay, in DSSS, bandwidth gets scaled by a factor q power k for some positive integer k, and magnitude of frequency response gets scaled by q power minus m for some positive integer m. I can tell you up to this much, then you have to go to the lecture and find out what is the value of k and m. So the options give you bandwidth gets scaled by q, that is, it gets scaled by q power 1, and magnitude gets scaled by 1 over q square, another statement, that is q power minus 2. So I can tell you that bandwidth gets scaled by a positive power of q, and frequency magnitude of frequency response gets scaled by a negative power. So it's 1 over q power m for some positive integer m. What are the exact values of k and m? You should go back and watch the lecture video to find out. Question 4 is, what is the bandwidth of a DSSS system with a spreading factor q equals 32 and symbol time ts equals 8 microseconds? Bandwidth is q over ts for a DSSS system. You have been given q and ts, you can find bandwidth from that using the formula. Actually, this is 1 over tc, which is q over ts. Next question is, what is the Symbol duration for a DSSS system with a spreading factor. Q is 32 and chip duration EC is 16 microseconds. And then 4 itself, I told you 1 over TC is Q over TS. So the symbol duration TS is Q times TC. Which of the following is an advantage of the DSSS system? I'll give you hints to solve this. So spreading codes we use in DSSS are very close to uncorrelated. What that means is only the corresponding user signal will have high energy when a multi-user DSSS signal is correlated with a particular user's heading code. So when you correlate the signal with a particular code, only the user who used that code, that person's signal will be highly correlated. The rest of them will be uh, highly uncorrelated. So effectively, Other users' signals can be treated as noise. So that should answer your first part, first option. Next hint is spread spectrum signals have amplitudes that are so low that they are comparable to noise amplitudes. It should imply that to intercept the signal, you'll need to know the spreading codes. That should answer whether B is correct or not. Then the rake receiver that we use takes advantage of the multipath components present in frequency selective fading. That should tell you whether option C is true or not. These are just some hints to answer the question, but the actual answer you have to find out yourself. We are given a pulse g of t is rectangle t minus t over 2 by t. The Fourier transform of g of t is So this rectangle, vector of t by t is the signal which is 1 from t by 2 to minus t by 2. Now we have a shifted version of the rectangle. First let's do it for the rectangle. A Fourier transform is x of t e power minus j 2 pi ft dt, but this only goes from minus t by 2 to t by 2. So t is 1 in that range, 0 everywhere else. E power minus j 2 pi f t dt, which is integral of uh, e power omega t dt is simply e power omega t by omega. So it's e power minus j 2 pi f t divided by minus j 2 pi f. So this becomes at t by 2, we'll take the minus 1 or j 2 pi f outside. T by 2, this is e power minus j 2 pi f capital T by 2 power minus j 2 pi f minus e power plus j. This is 1 over j 2 pi f e power j pi f t minus e power minus j pi f t. Okay, now further simplification I'll leave to you. So you have to write it in terms of, say, as you can see, options are all in terms of sinc function. Sinc function is a function of the form sine of theta by theta. So, and you know that sine of theta is e power j theta minus e power minus j theta by 2j. So, write this in terms of sine, then you'll get in terms of multiply and divide by t, then you'll get t sinc of something. Okay, then the next thing you have to know that is here the signal is not just rectangle of t over capital T, it's a shifted version. But if x of t has the Fourier transform x of f, then you can show that x of t minus some delay tau is x of f times e power minus j 2 by f tau. So time shift corresponds to a phase change in the frequency response. So shift in time domain is equivalent to a phase change because this factor does not change the magnitude of the frequency response. It only changes the phase. You combine these two things and find out the answer. In question 8, in the above question, the first zero crossing of the magnitude of g of f occurs at a frequency at what frequency? So um, solution is straightforward. In the Fourier transform, you see that um, in all the options above, uh, the only thing, so there are the options are of the form sink of something into e power something into t. In some of the options have capital T, some of them are not multiplied by capital T. But regardless, the in the magnitude, f is the quantity that is varying. The only way that function goes to zero, g of f goes to zero, is if the sinc function goes to zero, right? In the above question, G of f is of the form. Uh, it's of the form a sinc theta e power j omega for some a theta and omega. So the magnitude will simply be a mod sinc theta, the absolute value of sinc theta, because the magnitude of e power j omega is 1. Now, magnitude of GF is 0 implies since A is not 0 in any of the options, regardless of which of the options is the answer in the previous question. That means sinc theta is 0. And sinc theta is sine of pi theta divided by pi theta is 0, which implies pi theta is n pi for some positive integer n. So you have to find out at what value the argument of the sinc function multiplied by theta becomes an integer multiple of pi, and at that point the sine function is 0. Sine is 0 at all integer multiples of pi. And the first one among those points is the first point at first zero crossing. Assume two random sequences x and y, each length q. What would be the power of interference between these sequences when there is a unit lag? Rxy is 1 over q times summation L goes from 0 to q minus 1 x of L y of L minus 1. use that and find try to find the power of interference between these two sequences. Okay, I'll take a 2 minute break. I'll go to the restroom and come back. Okay, back to the question. Um, so general formula, if the lag is k, is Rxy of k is, and it's the expected value actually. And the interference power E is the expected value of the square of the quantity, and this will turn out to be, if you work it out. Now, this was for k is equal to 0, assuming this. Now they have given that there is a unit lag, that is k is equal to 1. So you have to work it out, and or if you can think intuitively, you have to uh, know whether the power of interference will change if there is a unit lag. That I'll leave to you. So does the interference power depend on the lag or not? Or if the lag is 1, will it change? How does it? You can go and see this in uh, the first lecture of week 10, I think. Okay, I won't say any more about that, but the k equals 1 change interference power. I'll leave that to you. Then consider m sequences with m equals 4. What will be the number of zeros and ones respectively in the sequences? Now go back and check in the lecture if what I am writing is true or not. Number of ones in an M sequence will be 2 power m minus 1. Number of zeros is 1 less than the number of ones. Then What will be the result of the autocorrelation of an M sequence with itself with zero lag? So we already saw if for two different sequences RxY, the correlation. Now Rx of k, the autocorrelation is with lag k is conjugate of L minus k, and this is mod q, and if the lag is 0, Rx of k is 1 over q summation 0 to q minus 1 x of L x conjugate of L mod q. And since L goes from 0 to q minus 1, so this was capital mod. Oops. mod q. Since L only goes from 0 to q minus 1, this is simply L. From this, that's almost the answer. Just one or two steps further, I'll leave it to you. Okay. At the end of the day, if you are unable to solve it further, then you can go and watch the second lecture of this week, of week 10, where the professor has actually solved it further. But it's best if you try it yourself once. In case you can't solve it, you can go and check the lecture. Okay. Consider the consider M sequences with M equals 4. Okay, this is next question is more of a conceptual question. To consider M sequences M equals 4, assume that all of the 15 different sequences are assigned to 15 other users. What can be a potential problem in doing so in a multipath environment? And the options are there would be no way of distinguishing between signals which are multipath of the same user from the signals of other users. Option B is system cannot handle multi-user interference. Option C is both A and B. Option D is none of the above. So think about it. If all the sequences are used for different users, so then if there is a multipath component from a user, then is it possible to tell whether it is a multipath component that is coming, or is it from some other user? So both of them are actually you can't really tell because you're using all possible sequences. So the multipath component will be one of the other sequences, and it will also be a sequence used by one of the other users. You can't really tell. So option A is actually true. Option B, the system cannot handle multi-user interference. That I'll leave to you. Check whether B is true or not. If B is false, then the answer is A. If B is also true, then the answer is option C. Then in question 13, which of the following statements is correct about scrambling and encryption in the context of CDMA? M sequences are used in CDMA 2000 for scrambling. Option B is reverse operation is easy for scrambling but hard for encryption. Both A and B, scrambling and encryption are different names for the same process. Again, this is just a conceptual question. You can go and see in the lecture video. But I can tell you that it's not option D. It's either A, B, or C. Next question 14. Consider the following diagram in the context of CDMA 2000. The output data rate should be 1.2288 MCPS. If the input rate 4.8 kilobits per second, the rate of the convolutional coder is what? So you have the input, and you have the convolutional coder, you have spreading width q equals 64, you have the output. You're given R3, R2 should be R3 by Q. Q is the spreading factor. Then rate of convolutional coder is R1 by R2. R1 is also given input rate 4.8 kbps. The numbers are such that the rate is valid rate. It's a proper fraction. Next question, which of the following equations denote the mutual orthogonality principle in DSSS? That you can, again, it's a conceptual question. You can refer to lecture notes 43, 44. Then, which of the four logic channels is used for channel estimation in CDMA 2000, pilot, sync, paging, and traffic? And again, conceptual question. You can see picture 45. And which of the following carries system information and information regarding PM sequences in CDMA 2000? Again, the options are the same. This also given in lecture 45. 18. Which of the following is a difference between WCDMA and CDMA 2000? Option A is WCDMA can support spreading sequences of variable lengths, but CDMA 2000 cannot. That's true. That is a difference. And WCDMA can support multiple chip rates, but CDMA 2000 supports only one chip rate. C is both A and B. D is neither. Now B is also true. That is also a difference. So in these two ways, WCDMA is better than CDMA 2000. I urge you to go and see the lectures and find out if Here, both options show that WCDMA can support spreading sequences of variable length and also support multiple chip rates. Find out if CDMA 2000 is better than WCDMA in any aspect. Question 19. For CDMA 2000, base station codes are separated by 64N codes where N is an integer. Consider N equals 2 and assume that 2 power 15 length short codes are used. What is the maximum number of supported base stations? There are 2 power 15 codes, and the base station separation is 64N, and that will be 2 power 15 by 64N will be the number of base stations. Substitute N is equal to 2 and you'll get your answer. Question 20. Consider the following statements for an orthogonal variable spreading factor code. Statement 1. If a code is assigned, its successor cannot be assigned. Statement 2. If a code is assigned, its predecessor can be assigned. You have to figure out whether both statements are true or false, or one statement is true and one is false. You can find the answer in lecture 45. And for orthogonal variable spreading factor code, um, if a code is assigned, its successor cannot be assigned. That is true. And if a code is assigned, its predecessor can be assigned. That is false. If a code is assigned, predecessor can also not be assigned. Then 21. Consider the following statements for orthogonal variable spreading factor code. Statement 1. OVSF of L, 2i is OVSF of L over 2, I, OVSF of L over 2, I. And statement 2 is OVSF of L, 2i plus 1 is OVSF of L over 2, I minus OVSF and minus OVSF of L over 2, I. Again, are both statements true or false, or which of them is correct? In this case, similarly, you can refer to lecture 45 and it turns out, and you can see that both statements are true for orthogonal variable spreading factor code. Then we have which final question, which of the following are primitive polynomials in GF of 2? 1 plus x power 4, 1 plus x cube plus x power 4, 1 plus x square plus x power 4, all of the above. So GF of 2 is nothing but binary field. Uh, Actually, we always work with binary, so don't need to know about fields to understand this. Uh, Here in GF of 2, 0 plus 0 is 0, 0 plus 1 is 1, 1 plus 0 is 1, and 1 plus 1 is 0. And multiplication, 0 times 0 is 0, 0 times 1 is 0, 1 times 0 is 0, 1 times 1 is 1. That's normal Boolean algebra. A primitive polynomial is a polynomial that cannot be expressed as a product of two factors of lower degree. And that's an irreducible polynomial. And it's called primitive if the roots of the polynomial don't belong to GF of 2. Now, okay, let me just write down the definition. Primitive polynomial, or GF Q is an irreducible polynomial that does not have any roots. A is 1 plus x power 4. Check what is 1 plus x square whole square. This is 1 plus 1 plus x square into 1 plus x squared, which is 1 plus x squared plus x power 4. So if this was in real number, if these were real polynomials, polynomials over the real field, then this would just be 1 plus 2x squared plus x power 4. But we have to remember that we are working in GF of 2, where 1 plus 1 is actually 0. So this is 1 plus 1 times x square. So this is actually 0 x square. So this is 0. So this is 1 plus x power 4. Therefore, 1 plus x power 4 is a reducible polynomial. You can write it as a product of two factors whose degree is such that both of their degrees is less than the degree of your polynomial. So here degree of this polynomial is 4. Degree of both 1 plus x square. So here simply writing it as 1 plus x square times 1 plus x square. Degree of both of these is 2. So we can actually express 1 plus x power 4 as 1 plus x square times 1 plus x square. So 1 plus x power 4 is a reducible polynomial. So it's not a primitive polynomial. Similarly, for option C, 1 plus x square plus x power 4, check 1 plus x square whole square. This is 1 plus x square to 1 plus x square. Of course, here instead of doing this, you can do one more thing. So if a is a root of a polynomial f of x, then f of a must be equal to 0 and vice versa. So if f of a equals 0, a is the root of f of x. Here you can see if x is equal to, if you plug in x is equal to 1, 1 plus 1 power 4 is 1 plus 1, which is equal to 0. So if you write f of x is equal to 1 plus x power 4, then f of 1 is 0. So 1 is the root of this polynomial. So even in that way, you can rule out that it is a primitive polynomial because 1 is a member of gf of 2. Here you can't do that because f of x is, if you substitute 0, then you will get f of 0 is 1. Substitute 1, you will get f of 1 is 1 plus 1, which is 1. So 0 and 1 are not roots of 1 plus x square plus x power 4. But it is a reducible polynomial. So let me do this multiplication. This is 1 plus x square plus x square plus x cube plus x square plus x cube plus x power 4. Since we are operating in gf of 2, this x and this x cancel out. These two x squares cancel out. X cubes cancel out. And you are left with 1 plus x square plus x power 4. So 1 plus x square plus x power 4 is reducible. 1 plus x power 4 is also reducible. And you can check 1 plus, then check whether 1 plus x cube plus x power 4 is irreducible and whether 0 or 1 is a root of 1 plus x cube plus x power 4. I'll leave that as an exercise. If it turns out that it's irreducible and 0 and 1 are not its roots, then the answer will be option B. It is a primitive polynomial. Otherwise, anyway, actually, fourth option is all the above, which is also not true, and we already saw A and C are also not true. So B must be a primitive polynomial, but you should verify it yourself and check whether there is any mistake in the options or whether it is correct. And there is no real other way to check if it is irreducible or not. You can use some tricks if you know finite fields. Otherwise, you have to write down all the So how you check is you write down all the polynomials of degree less than 4. That could be 1 plus x cube, 1 plus x square, 1 plus x square plus x cube. You have to write down all of those. Other than 0, 1 and 0 and 1, which are constant. And then you have to check whether you have to divide 1 plus x cube plus power 4 by each of those polynomials and check if any of them divides 1 plus x cube plus x power 4. None of them divide this, then it's an irreducible polynomial. Otherwise, it's reducible, whichever polynomial divides it. Only thing is, that's a very complicated, very time consuming. So sometimes you can use small tricks to check it. For example, if this was divisible by x, 1 plus x cube plus x power 4, then x is what? X is nothing but x minus 0. So if, again, if f of x is divisible by x minus a, then uh, a should be a root of the polynomial, which means f of a must be 0. So to check if it is divisible by x, can also be written as x minus 0. So it is enough to check if 0 is the root of 1 plus x cube plus x power 4. It's not. So you can say x does not divide 1 plus x cube plus x power 4. Then you can see that x into 1 plus x, which is x plus x square. This is also a polynomial of degree less than 2. But if x plus x square divides 1 plus x cube plus x power 4, that means x into 1 plus x divides 1 plus x cube plus x power 4. That would mean um, both 1 and 0 must be roots of 1 plus x cube plus x power 4. So if you already have checked whether 0 and 1 are roots, then if they are not the roots of 1 plus x cube plus x power 4, then that means x plus 1 and x plus 0 are also not factors, which means that x plus x square also does not divide 1 plus x cube plus x power 4. So you no need to check by division whether x plus x squared divides 1 plus x cube plus x power 4 or not. So these kind of tricks you can use and check whether your polynomial is irreducible or not. Anyway, in this question, we already checked option A, C, and D were wrong, so option B must be right. But in general, that is the method. All right. That is all for today's session. I'll see you in the next session 2 weeks later.